and welcome to this video. In this video, we're going to be looking at the topic of wave-particle duality. So this is quite a strange idea in physics to get your head around. It's definitely one of the things that physicists themselves are very not happy with, purely because it just means all of our models of light aren't exactly accurate, because we can't use one single model to be able to explain what light does. We have to refer to two models and say that light can be either of those things at the same time, but we're not exactly sure which one it is. And so in the case of light, we know that light can be a particle in the case of a photon, or it can be a wave in the case of, well, waves. Okay? Like an electromagnetic wave would probably be what we put, an electromagnetic wave. Okay? This was a pretty accepted idea for quite a while, but then in the 1920s, a man named de Broglie, so people tend to pronounce this name wrong a lot. People tend to say de Broglie, but the way it should be pronounced is de Broglie. So just don't get confused with the way I pronounce it. But de Broglie had this idea. He said that surely if light can behave as both a wave and a particle at the same time, why can't all the other particles behave as waves? And so he set out to prove that all particles can have wave properties as well. And so what he did is he said that we know for a fact that electrons are particles because we've always treated them as particles. They can have collisions. So we know we have electron collisions, and we don't have wave collisions. So therefore, they must act as particles. But this idea as what behaves as a wave, our wave evidence for light, so our evidence for particle nature of light is the photoelectric effect. And our evidence for the wave nature of light is called diffraction. Okay, now diffraction is a phenomenon that we haven't met yet. This will be in the waves topic. We will go through what diffraction is, but in a general sense, what happens in diffraction is we get two light waves interacting with each other to cancel each other out. So if we have two waves that interfere with each other, they can actually cancel each other out so that we get no resultant light at the end of that interference. And so de Broglie said, what if we can do electron diffraction? Okay, so electron diffraction. And what we saw with electron diffraction was that the same thing happened. We had electrons that were cancelling out other electrons and forming no resultant electron. Now, the only way we know that we can cancel out electrons is by annihilation, but there were no positrons there, so we couldn't have had anything annihilating, which means the electrons must have acted as waves. So now we know that these can also act as waves. We can also do this with protons. We can have proton collisions in particle accelerators. We can have proton diffraction. The only way we need to get it to be diffraction is by accelerating it. So this was kind of the genius that led to this idea that all particles can behave as waves and all waves can behave as particles. Okay, so they're constantly changing between them. Obviously, we know at a large, like, classical mechanics level, particles behave as particles and they can't behave as waves. But in a quantum sense, this isn't really true. In quantum sense, particles and waves can happen simultaneously. There is an equation for this, but I'm going to go a separate route to prove that this equation works. And I'm going to use the idea of light. And I know that light has momentum, okay? Which, for something that doesn't have mass, shouldn't be possible. But one of Einstein's equations, you will know, is that E is equal to mc squared, okay? But this is only part of it. This only refers to the mass energy. It's not the total energy of the particle. In order to calculate the total energy of the particle, we have a second equation, which is E squared is equal to P squared C squared plus M squared C to the fourth. Now this equation you do not need to know. Okay, this is not a necessary equation for you to know, but I'm going to use it here just to get this idea that we can derive de Broglie's equation from the principles that we know about light, okay? Because we also know that light is equal to hc over lambda, okay? Now, m here is the mass of a photon. A photon doesn't have mass, so this whole term becomes 0, okay? We can then square root both sides here and say that the energy is equal to the momentum times the speed of light. But that is also equal to hc over lambda, so therefore P c is equal to hc over lambda, and then we can cancel out a c on both sides, which leads to P is equal to h over lambda, where P is momentum. Okay, now h is Planck's constant, P is momentum, and lambda is the wavelength, which means as long as something has a wavelength, it can have momentum. Okay, so it doesn't actually have to have mass at all. All waves can have momentum, which is quite an interesting thing. It allows us to do a lot of things. Solar sails, for example, we can set spaceships up with large reflective surfaces so that when electrons collide with the sail and get reflected, their momentum is transferred, so we can use just light from the sun to propel spacecrafts through space. It's obviously still not going to be enough momentum to go very, very quickly, but it will work, in theory. Okay, so this is wave-particle duality. So this is de Broglie's relationship. Now, this in your formula sheet will come up as also saying that the wavelength of something is equal to h over mv, which is equal to h over p. Okay, now this is just this rearranged, because the wavelength, this is what we call the de Broglie wavelength. Okay, the de Broglie wavelength just refers to what is the wavelength of this particle if it was to behave as a wave. Okay, so if it's moving with some velocity and it has some mass, we can just do h over its momentum, and we'll get the wavelength that it would be if it was behaving as a wave. And vice versa, we can get, if we know the wavelength of the light, we can then do h over that wavelength to then get the momentum of that light. So this is the idea of wave-particle duality. Okay, so every particle can behave as a wave, and every wave can behave as a particle, and we have this relationship between waves and particles through this relationship between momentum and wavelength. I do want to go into something a little bit more interesting with this. Okay, this is not on the spec, but it is something that I think will probably pique your interest in this. So let's take this idea of electron diffraction, and let's just see how strange wave-particle duality is. So this seems a little tame, so let's take it a step further. So if we're looking at electron diffraction, okay, so we look at electron diffraction. Although you don't know, or you might not know the process of diffraction yet, this should still be quite a strange phenomenon. So for a diffraction to happen, we have to pass light through two slits, and it will have an interference effect on here. So we'll get maybe like a big dot here and then loads of smaller dots on the edge. Okay. Which is a weird thing in itself, but we'll explain that when we get to waves. Okay. So what we're saying now is, let's, instead of having light traveling through, let's have electrons traveling through. Now the electron, we know as it behaves as a particle, can only travel through one or the other. But when we are not looking, the electron can actually travel through both of them at the same time. Okay, so if we don't observe the electron, so we don't know which one it's traveling through, then we see this diffraction pattern. Okay, which means it's behaving as a wave. Behaves as a wave when we're not observing it. Okay, but let's say we had a laser that fires in a photon and fires in loads of photons, and if the electron is about to travel through here, let's say we had a screen here, if the electron is going to travel through there, it would reflect and it would go up to here, so we'd see a dot on the screen there, and if it was to go through here, then we would see it reflect and it would go here. Okay, so we'd be able to therefore determine which hole the electron is going through. And as soon as we observe it to say it's going through one hole or the other, we no longer see this diffraction pattern. Instead of all of these dots, we just see this dot here and this dot here from where the electrons actually travel through. But we don't see any other interference pattern. So when we're observing, it behaves as a wave, it behaves as a particle. Behaves as a particle when we are observing. So this is when we are not observing, this is when we are observing. Okay, but as soon as we take this apparatus away, as soon as we stop observing it, so we have none of this, and we don't know which hole the electron goes through, then we see a diffraction pattern again. We get a central fringe and then loads of little dots on either side. Which means somehow this electron knows when we're looking at it, and it knows then to behave as a particle, and knows when we're not looking at it and then to behave as a wave, which is a very, very weird thing. And hopefully this puts into perspective a little bit how crazy quantum physics can get, because I know a lot of sci-fi shows say, oh, it's quantum mumbo, whatever. Quantum physics is actually very strange, I guess, and this is why loads of sci-fi shows use the word quantum to explain anything that doesn't make sense, because they're just like, quantum will sort it out. But yeah, hopefully this piques your interest a little bit and you want to read a little bit more into this, because it is an interesting concept. But what you actually have to know for your A-levels is this bit up here. Okay, so basically this equation and the idea that we have evidence for both wave and particle natures of all particles. Okay, so this is wave-particle duality. Hopefully this is interesting and makes sense. Thank you for watching.